Welcome back. Hope you guys are doing very well. It's a beautiful sunny day here, and we're going to be learning about another very interesting string matching algorithm, which is based on the similar concept of finite automata, which we discussed in the previous lecture. So what it is? Knuth-Morris-Pratt, three scientists, wonderful algorithm. So what it is essentially, so in finite automata based string matching algorithm, if you remember, we discussed about a transition function table. Okay, so we construct a automata based on what pattern we have and try to come up with a transition function that on each character what my finite automata machine will give me next character. So some kind of pre-processing of the pattern. Okay, so after pre-processing of the pattern, string matching is very simple. It's in linear time. So time is spent is basically constructing that transition function table. So we discussed transition function delta in the previous lecture. Okay, now extending that concept beyond that, where we can make use of knowledge associated with the pattern. Okay, so in the plain transition function, we took each character, okay, and we mapped that. Okay, if I'm in a state 1 and the character E comes, okay, as an input, on which state I'm going to be moving. Okay, so I'm taking that decision plainly. I'm not making use of how the pattern is matching with itself. So that's the key idea, how the pattern is going to match with itself. All right, so that key idea or key information, if we can make use of that, okay, the pattern has a certain characteristics that EFE is, or EF is repeating itself, EF. So we can make use of that information or that knowledge associated in the pattern to reduce the comparisons, okay, or to reduce the number of transitions if we talk about transition function table. Okay, so that's the basic idea, and here we are talking in terms of a prefix function. A prefix function which encapsulates knowledge about how the pattern matches with itself. So in this typical example that we have this text string and a pattern string. All right, now in this typical example we say that the pattern is matching only up to the Q characters, okay, after the shift S, but it doesn't match up at the G and E locations, okay, at Q plus 1 and Q plus 2 locations. Now finally the pattern doesn't match with the text, okay, after the shift S, but even though if it doesn't match, but we have to do the comparisons for E, F, E, F, E, these are matching, but G and E doesn't match. So whole we have to do comparisons for all the characters here. Okay, but what if we know that, okay, some information that, okay, up to Q number of characters it does match. So we already know that information, and if somehow we can store that information or make use of that information, that, okay, we know that up to these many characters my pattern is going to match with the text, only I have to compare G and E and see whether these two characters matches or not. So I can reduce down the comparisons significantly. All right, so what essentially it means to say that, let's say if I shift or if I try to match up the next character, okay, that is F, okay, and F is matching with F, okay, so E and F matches with E and F. All right, now if I go little forward and if I try to match up with the S plus 2, okay, means 2 more locations where I was matching the character with the shift S, then what happens that I can say that okay, three more characters are matching, but not after that. So if I make a shift S to S plus 2, so I can say okay, E, F, E are matching, but not the rest of the characters. So essentially what I did here, I reduced down a comparison by 1, because in a regular sense, when your character or your pattern doesn't match and you exit at the G, then you have to start again from the S plus 1 location, okay, and you have to do the same process again, okay, and then you have to start from the S plus 2 location, you have to do the process again. Now if you start from S plus 1, then you match with the E with the F. Doesn't match, you just exit, then you move on to the next location, then you say E and E at the location F S plus 2 are matching, okay, good, then F and F is matching, good, and then E and E are matching, good, but the F and E will not match, so this will not match, okay, but you have to compare these two characters or these three basically characters again, right? So we sort of, if we know in advance that okay, we know that these are gonna match, but then we can avoid the matching of these characters and we can just simply jump, or in other words we can say that we are trying to find this shift S which satisfies this equation, okay, that new shift S, okay, so we directly jump in the text string with the S tick which satisfies S tick plus K is equal to original position where we were, S plus Q, how many characters matched up in the previous step. So that's the key idea of this algorithm, right? Or you can also say that new shift S tick would be S plus Q minus K, where S is the previous shift and Q is the characters matched up in the previous step, okay, and the K was gonna match up, how many characters are gonna match up next. So it's sort of, we are trying to find or we are trying to make use of the information embedded within the pattern itself, that the pattern is matching with itself, okay. So now let's see how the algorithm works in practice. It's a very simple algorithm. So algorithm for matching is very simple. Once you have that prefix function computed already, so you have in this array or data structure pi, you have or the output of this function is stored in pi compute prefix function, okay, and that prefix function will take your pattern, actual pattern, all right. And after that, once you have that, you just match character by character, okay, the text string. So you process the original text string in a loop, and Q is some variable, and you just start matching it up. And if you notice here, see this condition at 5 and 6 and 7 and 8. So here see Q is incrementing only at line number 8, and that too under if condition, okay. So essentially we are trying to analyze that what's going to be the complexity of this algorithm. So this sort of, if we talk about the amortized case analysis, then it turns out to be that in the order of n, okay. Very simple, that you start matching. If your pattern at the location q plus 1 doesn't match, then what it is that you update the value of the q, what is in the prefix function table, and if it does match, you increment the q. And once you finish the or at any stage in your processing the text string, if q equal to m means at that point the pattern matches with the shift I minus m, okay, and then you update the value of the q with the prefix function's value. Now we're going to be looking at these prefix function in a table, okay. on the next page when we're going to be discussing an example. Okay. And compute prefix function is simply you process the actual pattern, okay, and with that pattern you store what is the mapping, okay, in a table or in an array pi, which is kind of prefixed array, and you store the locations. Okay, my pattern matches with this location pattern, okay, and same way here, one for loop and one while loop, okay. And if we talk about the amortized case analysis for the compute prefix function, it turns out to be in the order of n as well. All right, turns out to be, it turns out to be in the order of, sorry, m, okay, because here we are talking about pattern, and pattern has the length m, so its analysis turns out to be amortized case analysis in the order of m. All right, these two algorithms are very similar, okay. So while loop makes sure that, okay, I'm trying to calculate the prefix function, okay, and based on that I'm going to be updating the new location, okay, for the value of the k, and then at line number 5 I'm just matching it up, okay, the k plus 1 location and what is actually at the q location, the pattern, okay. So I'm trying to find out the match of the pattern's character with itself, how it is behaving, and then I'm keeping on updating those values or of the k in an array pi, which is my prefixed array, okay. Now let's talk about an example, because without example it is difficult to understand. All right, so let's talk about an example. So first let's see how the compute prefix function is going to work, okay. This is a typical very simple text string and pattern strings I have been using in these lectures, but nevertheless the same procedure you can apply to a complex string. All right, let's talk about the prefix function, how it is being calculated. All right, now you see here the pattern is EFE, so we have I is indicating the index, pattern EFE, one location E, second F, third E, and then let's see how the pi is being calculated. So if you see here, we initialized pi 1 to 0, okay, and k variable is 0. Now for q equal to 2 to m, all right, while k is greater than 0 and p of k plus 1 is not equal to p of q. Now here k's value is 0, so we jump onto the line number 5, because here we need to satisfy k is greater than 0, so we are no longer here, we are here. Now we want to check what is the value of the pattern at k plus 1, which is 0 plus 1, so the value of the pattern at 1 is E, whether it is equal to the value of the pattern at q. So pq, what is the q? So q here is 2, and value of the pattern at pq is f, okay. So E is not equal to f, okay. So then we don't increment k and we return pi of q is equal to k. So pi of q is 2 is equal to 0. All right, now we move on to q equal to 3, q equal to 3, good. Now here k is still 0 because we did not increment the k, so we are no longer at line number 3. We move on to the line number 5, p of k plus 1 means p of E, p of k plus 1, k is 1, p of 1 is E equal to p of q. Here q is 3, okay, location 3. So pattern at location 3 is the character E. E and E matches, so we satisfy this condition. So we increment k equal to k plus 1, okay, and then value of the pi q is 3, is k is 1, means pattern is matching with the location at 1, okay. So pattern at location 3 matches with the pattern at location 1. Very simple table. So same way, if you have a bigger pattern string, you can compute the prefix function table. All right. How the pattern matching algorithm, KMP matching algorithm works. After we have calculated the prefix function, now let's talk about on our typical example how it's going to work out. So as you can see here, I have this little table which describes the index and text string and the variable q, which we're going to be using in our KMP matcher algorithm. So we initialize q with 0, and at line number 4 we have this for loop which goes for the whole length of the text string, and then here we take a decision. Okay, if q is greater than 0 and p of q plus 1 is not equal to t of I. So let's talk about q. Q is 0, so we don't go to line number 5, okay, and we don't execute line number 6 as well because this is under this while condition. We go to line number 7 and try to see if the 7 matches. So p of q plus 1 means p of q is 0 and plus 1 1, p of 1 is e. Okay, whether it matches with t of I is here 1, so I is 1. Yes, these two matches. So what we're going to do, we increment the value of the q to 1. Good. And now if q equal to m, then we say pattern occurs with a match I minus m. Okay, and then we increment the q accordingly, but q is not equal to m. Here m is 3. Okay, here m is 3. Okay, how many characters we have in our pattern? Okay, that is the m. Now we go to the next I value, which is 2, and now here at the 2, when I is 2, okay, and q is 1, so we basically going to be executing line number 5 and try to see if p of q plus 1 means p of q plus 1, q is 1 is p of q plus 1 f. Let's see whether f matches or doesn't match with t of I. Okay, so f doesn't match with the e. Okay, f and e doesn't match, so we satisfy this condition at line number 5 and we update the q value of the q equal to pi of q. So what is the pi of q? Q is here 1, pi of 1 is 0. We update the value of the q to 0 and we move on to the next I value, which is 3. Okay, so now let's say q is 0, we don't execute line number 5. Now here at line number 7 we try to see q is 0 plus 1, that is 1, so p of 1 is e, whether it is equal to t of I, which is 3, is f, so e doesn't equal to f, so we just don't execute it, value of the q remains 0. We move on to the next text string at location 4, I equal to 4, same thing occurs. We don't execute line number 5, we try to execute line number 7, try to see the condition whether p of q plus 1, which is q is 0 plus 1, so p of 1 is e, e is equal to f, no, so that's it, doesn't match here, doesn't match here, so q value is still 0. Now we move on to I equal to 5. Now you see here, when I equal to 5, t of I is e, matches with pattern. When it matches with the pattern, we simply increment the value of the q at line number 8. We move on to the next one. Now the value of the q is greater than 0, so we're going to be executing line number 5. Okay, so q is 1 greater than 0 and p of q plus 1, p of 1 plus 1 2 is f. Okay, here f, whether it is equal to t of 6 I, which is 6, means f, then we increment. Okay, we increment the value here because this condition at line number 5, because it matches, so we don't execute this line number 5, neither 6. But since it matches, we execute line number 7 and 8, and we increment the value of the q to 2. Same thing we do when I equal to 7. Okay, we increment the value to 3. Now see here, when the q becomes 3 is equal to m, then we say pattern is now matching. Good. So we matched up at that point. So it's a very simple execution. Now if you try to do amortized analysis of this algorithm, it will turn out to be in the order of simply, it's a bounded complexity in the order of m. Okay. So somehow magically these loops, you see, they don't contribute to more steps. They just have a bound there, which is bounded by number m. Number m is how many characters or letters or alphabets you have in your pattern. So good, it's a better algorithm compared to finite automata based algorithm. However, concept is similar, but it is making use of the information how the pattern is matching with itself to avoid unnecessary comparisons. A bit faster. All right. Thank you very much, guys. I hope you have enjoyed this lecture, and thank you for your wonderful comments. And if you need any help, any support, or any other kind of lecture or any other subject, to let me know. And those who are new to my channel or who haven't subscribed this channel, please do subscribe. This way you will get notifications as soon as I upload new videos. I hope these lectures are contributing to your learning.